mouth gets so dry.
Good afternoon, everybody. I'm Stuart Wheeler, and I'm with the Fighting Salmon again. It's the last time you're going to see us. You're very sad. Because I'm going to miss you guys. But we're going to talk about a little bit about the background of our system, some review of what we've done in the past, the steady-state operating curve, the step response, the sign experiment, and the Bode plots. And we're going to move on to the fun stuff, the proportional only modeling and the experiments and about that. Duct cooling system. We have ducts and we cool them with that motor right there. We have heating elements inside the ducts to heat up the air, and we control the power input percentage to this motor and trying to adjust the temperature output within those ranges with both dampers closed. Our steady state operating curve, we've got, we have our output can be found with -2 times the input plus 150. This is an example of our step response with the PDT modeling. The gain on this particular one we found to be -0.29 degrees Celsius per percent with basically 0 dead time and a time constant of 0.5 minutes. This is an example of a frequency response. We would use these, lots of these, to make the Bode plots for the phase angle and the amplitude ratio. This is one of our Bode plots for the amplitude ratio. We use this to find the gain, the controller gain, the ultimate frequency, well, the ultimate frequency for the phase angle. But for this one, we found I forgot to put it up there, but the gain to be 0.78 degrees Celsius per percent. For our phase angle Bode plot, it's kind of crazy. I'm not really sure what happened, but for this one we found the ultimate frequency to be 18 hertz and the ultimate controller frequency, gain, to be 10% per degree Celsius. And now for the fun new stuff. We use MATLAB to plot this. A little bit better than Excel, but we're going to focus on 3 things here: the gain and at the ultimate controller gain over there at the far right. Because by the way, everything in that blank section past 0 is bad. It's bad. This will make your machine explode, or so says Dr. McCullough. But we're focusing on the critical damping, the quarter decay, and the ultimate controller gain. And the ultimate controller gain from this Rouleau's model we found to be 5.7, and then 3.8 for the quarter decay, and the critical damping is 0.35% per degree Celsius. This also, when we apply it MATLAB, it gives you the damping ratio for each of these. There is no damping ratio for the one towards the top because it is basically 0. For this plot, we use the gain to be -0.78 degrees Celsius per percent with a time constant of 0.07 minutes and a dead time of 0.04. Okay, here's the model for the critical damping. It's boring, but for this we found a controller gain 0.4% per degree Celsius, pretty good bit of offset, 1.5 degrees Celsius. Well, it looks worse on the graph than that actually. It's 1.5 degrees is not. And this one's a bit more interesting with the quarter decay. The overshoot should be 51%. That corresponds with the Rouleau's plot there. And the controller gain for this one was 3.8% per degree Celsius. For the ultimate controller gain, found to be 5.8% per degree Celsius. And for the experiment, we had a fun time with the experiment. We ran it like 30 times, literally 30 times, and we kept getting different values to try and find the set point. So I picked, just arbitrarily picked one just kind of based off of the SSOC graph. I chose the M bar to be 55%, which was the set point is 47 degrees Celsius. We just kind of went with that, just so I'd have something to show you. And and we put the controller gain at the critical damping at negative 0.4% per degree Celsius. It stays pretty steady. On the bottom is the output in degrees Celsius, and the solid line across the middle is the set point. And on the top is the input percent. And it kind of stays fairly level. It's not doing anything weird, which corresponds with the model. The model is pretty stable, and so is this, which would be a good thing if you wanted to keep your system at the same temperature for a long time. This would work well. Say your control panel. Quarter decay got a little more interesting. It oscillated for a good while. It didn't really level out much at all. That negative 3.8% per degree Celsius for the controller gain. You might not want to set it there because your output is, well, I mean, it looks bad on the graph, but in reality, this is only like a 1.5 degree difference. So it's also still good. The ultimate controller gain experiment we had at negative 5.8% per degree Celsius. It oscillates another again, but I had to zoom in a lot for it to do anything on some of these. But this one, it's getting worse, and it's still not that bad though. It's a couple of degrees difference in the oscillation. So unless you need to control something really specifically, this still might not be a huge problem. And then I want to do something really crazy. So I set this at negative 50% per degree Celsius, just to see what would happen. And the controller goes nuts. The input percent is just everywhere. It's all over the place. But what I found interesting about this was that, because it's changing the temperature, it can't respond fast enough. So it actually keeps it really steady. The controller's going nuts, but the temperature stays really steady throughout this whole thing. So if you wanted to keep your temperature the same, you could either set it really low, like at negative 0.4% per degree Celsius, or you can set it really high. You might not want to do that. It might wear out your parts eventually, but that's either one seems to work pretty well. So we've gone over a little bit of the background of our system, looked at the previous work with the steady-state operating curve, the step, sign response, the Bode plots, and the proportional only controller modeling and experiments. And I appreciate your time. And
anybody else today?
Got to read my suggestions to improve and tell them, man. It really hits home.
Does it? Thank you. There's Salmon. Hey, you. Salmon. Where's Lavender? Hey, there you are.
You should get excited.
Merry Christmas.
Oh, thanks. I drew with a big bite like he was flexing or something. Go on.
I think it really is. All right, it's time for a wake-up call. Wake up, wake up. Here's my score sheet for today's presentations. 4 presentations. 3 zeros. Because not all regions of your SSOC were presented in the results for modeling and experiments for proportional control. If you don't present the results for modeling and experiments, your customer isn't getting what your customer wants. All 3. Yes, sir.
What happens if one of your team members hasn't done their portion?
That's unfortunate. What happens if 2 team members haven't done the modeling and the experiment? That's unfortunate. But your customer is not getting what your customer wants. Now, you want to do all 3 or just 2? I would. I'd talk to your team member, look at your team agreements. Now, those people that got zeros, what do you suppose they're thinking? Can I do it again next week? Suppose everybody's thinking that? Erase this 0? Be all right with me if you want to. But do all 3 experimental feedback, proportional control results. All 3 proportional control modeling. And B, when you describe what your K, tau, and T naught are, I believe I said we're going to use frequency response results for that. So I want you to show me K, tau, and T naught that you got from your frequency response for each region. What are you thinking? What are you thinking, Ethan?
I didn't present today, so I'm all right. I didn't present today, so I'm all right.
What are you thinking, Alex? No, not Alex. I understand. What are you thinking, Ron? Same mode. What are you thinking, Morty?
I can do better next week.
Jerry, what do you think?
I've got next week's presentation, so I better have all the information there.
Think you better. Who else has next week's presentation? Probably 3 or 4 more. Yeah. All right, so maybe it's time to talk in your team and decide what you're going to do about supporting each other. 5 minutes? Go.